Hi guys. How you doing? So today, basically what I'm going to do today is just answer questions about homework problems. So you guys, let me open up my chat window here. Let's see. So what we can do is go over homework for 2.9. We have a quiz today on 2.9, right? That starts at noon today, right? It opens up. It's a 24-hour availability window. And then the homework for 2.9 is due at midnight tonight. Appendix A, I can also answer questions about. That's due next week. Hang on, maybe a bit some people. Appendix A is due next week, but you're also free to ask me questions about that. If you'd like to ask about the exam, I can go get my notes and we can talk about that too. But in the meantime, this is basically kind of like if we were in class in person, then we would just be going over the homework problems for chapter 2.9 if you guys had any questions. And then if you guys don't have any questions, I might, choose a homework problem or two just to kind of go through it. But basically, this time is for you, to ask questions on the homework to help get you prepared for the quiz. So you guys can put it in the chat or you can ask me, you can unmute yourself and ask me, but anybody have any questions on the homework for 2.9 or Appendix A? Okay, 2.9, number 47. Let me see. Give me okay, is this the tangent line problem? Okay, so this is chapter 2.9 question. That's in focus. Okay. So let me draw a picture. So this is chapter 2.9, number 47. Let me draw the picture out for it so we can visualize. So we've got this y equals x squared parabola. This is y equals x squared. We've got x naught, happening here. We've got the tangent line. Tangent line kind of cuts down right here. Oops, I did onto my hand. Right here at our x naught. And then at this point here, we have there's theta is right here. That's theta. Okay, so this is our tangent line. And this point is x naught comma x naught squared. Okay. This is x naught squared in order to get a feeling for like what we're dealing with here. Okay, so let's go through and start thinking about what they're asking here. So part A says theta is the angle of decline. So that's like where our tangent line basically hits our curve, right? And they want that, we want theta as a function of x, okay? So what I'm going to do is I'm going to write a couple things down here. Let's see, what was the question? Because this is what I have. I just have my notes here. X is greater than or equal to x naught. Y equals x naught squared. Let's see, I don't know. Why don't I have, I don't have more on here for that, but let me, oh yeah, here we go. Okay, so so the slope of the tangent line of y equals x squared, right, is our derivative, which is 2x, okay? There. Our derivative 2x, and then we're doing this at our point x equals x naught. Okay, so this is in quadrant 2. So x is negative, right? So we have minus x naught. So whatever x naught is, it's a negative number. So basically we're looking at tangent of theta equals minus f prime at x naught, right? So we're looking at like this right here, okay, which is equal to minus 2 x naught. Minus because this x naught is going to be a negative value. So it's basically like we're looking at f prime at x naught, okay? And it's negative because x naught's going to be a negative number. And you can kind of see that in our graph, right? Our tangent is a negative sloping line, so it's minus 2x. Okay, this is tangent of theta equals minus 2x naught. So if we solve for theta, theta equals the inverse tangent of minus 2x. Okay, so that comes from our graph, and we're thinking about opposite and adjacent. Okay, right now, and then B says, what is d theta dx? Okay, so that means I'm going to take this derivative right here. So I'm taking the derivative of my inverse tangent function. So I've got a couple things. I have chain rule that I have to worry about, and I've got this minus 2x as an inner function. So whenever I do any kind of like x squared on my inverse tangent derivative, I have to do minus 2x quantity squared. This is going to be 1 over 1 plus minus 2x quantity squared times minus 2, right? This minus 2 comes from our chain rule. So I'm just going to clean it up. That's minus 2 all over 1 plus 4x squared. And then we're looking at when x is equal to minus 1. So it's going to be equal to minus 2 all over 5. And we can see it that the tangent line, oops, sorry, not tangent as a function, but tangent line has a negative slope at x equals minus 1 there. Okay. So that's 47. I'm going to do the 2.9 questions first, and then we'll go on to Appendix A. Okay, so hold that thought. So 2.9, question 27. I'll take a look at. What did I have? Oh yeah, okay. You guys have all this here. I'm going to scroll up. Right, so now we're going to do question 27. This is from chapter 2.9 as well. All right, so what we're given is sine of the inverse sine of u equals u. Cosine of the inverse cosine of u equals u also. Okay, so keep these in mind when we're doing this stuff. These are like true false problems. And I want to give some kind of an explanation for like what this is. I think if you have like an answer to this, I think they just said true or false, but you want to like know why. All right, so question A, part A says we've got the sine of the inverse sine of 1.5 is equal to 1.5. And this is false because the domain, the domain of the inverse sine of x is equal to -1 to 1. So even though technically it's true, like even though this is true, right? The inverse sine of u, even though like it seems like I should be able to just do u substitution and then substitute that in, this 1.5 is actually outside the domain. So if I were to actually take the inverse sine of 1.5, I would get a domain problem. Okay, I would get a domain error. So I can't even get past this inner function, okay, in order to get out what that is. I can't just kind of look at the big picture and say, oh, this is, you know, sine of the inverse sine is equal to u. I have to make sure that this value on the inside satisfies my domain for that function. So that's why it's false. Inverse sine of the sine of 1.5 equals 1.5. Okay, so now I've got sine of 1.5. So remember, this is in radians, right? So true, because the domain of the sine of x is all real numbers. Okay, so I can have any value I want as an input to my sine of x function. So 1.5 is within domain of sine of x. Therefore, we can take the inverse sine of whatever the sine of 1.5 is, right? So you can kind of think about it as I'm going to take the sine of 1.5, that's going to be a number, and I'm going to plug that into my inverse sine function, right? Because my sine is going to give me an output that's between -1 and 1, which will satisfy the domain of my inverse. Okay. See? Cosine of the inverse cosine 1.5 equal to 1.5. Okay, this one is false because the domain, again, domain of inverse cosine of x is equal to -1 to 1. Okay. And D says cosine no inverse there, cosine of 5. And this is true here because the domain of the cosine of x is all real numbers. So you can take the inverse cosine of whatever, like this is going to be the cosine of 1.5. So it's going to be a number. Invert, like cosine of 1.5 is going to be a number, and that number is going to be between 1 and -1, right? That's my output for my cosine function, which satisfies the input of my inverse cosine function. So you have to look at the domain, right, of my sine function, right? And I have to look at the domain of my inverse sine function. Okay, so my inverse sine function, like for C and for A, my inverse sine, my inverse cosine function, these values here are bombing out of my bombing out of my domain. So think about like when you do composed functions like f of g of x, you have to evaluate g of x, your inner function first, right? Get some kind of a value. And if that value bombs the domain of like my greater function, then it's not going to work. If that value, whatever I'm putting in as my input is going to bomb my inner function, the whole thing's going to bomb out. Okay, so you've got like multiple steps where you have to check to make sure that it's not going to violate your domain restrictions. Okay. Let's see, 97 and number 21. Mm, 21, okay, great. You guys will have this thing in a, turn the page. We're gonna do question 21. Okay, so question 21 says, we've got f of x equals inverse sine of x, and we're looking for inflection points, which implies that I need to be doing the second derivative, right? So my first derivative is going to be 1 over radical, remember it's 1 over radical 1 minus x squared, but I'm going to write it like this, 1 minus x squared to the -1/2, right? So I can do the power rule on it because I have to, oops, sorry, I have to do the second derivative on it. So I'm going to get it set up for my power rule. So my second derivative says I'm going to take the derivative of this. So I'm going to go -1/2, right? That's this. 1 minus x squared to the -3/2 times my chain rule minus 2x. Okay, so let's clean this up. I have a minus times a minus becomes positive. 1/2 times 2 becomes 1. This is x all over 1 minus x squared. This is 1 over, like that's why it's in the denominator. So 1/2 makes it a square, but I've got this raised to the 3rd power. Okay, so it's x over radical cube, the cube of 1 minus x squared inside the radical. Okay, so the inflection points, I have to set this equal to 0. You know, be careful, right? We're used, and we have to solve for x. So I'm used to thinking, right? I've got to figure out all my different factors, but I can't do, so the denominator cannot be equal to 0, right? So I can't set my 1 minus x squared equal to 0 and then solve for it, because look at a divide by 0 error. I don't want to introduce that. So we're basically just looking at where's our numerator equal to 0, and that happens when x is equal to 0. Now, when we check our second derivative, we see it changes sign at x equals 0. So therefore, it's an inflection point. Okay. That's 21. Okay. So those are, whoops, sorry, questions for 2.9. I'll give you guys a minute to write that, and then we'll talk about a couple problems from Appendix A. The first question is number 2. Okay, so Appendix A, question number 2. So let me write down what the problems are. X of t equals t squared minus 7. Y of t equals 5t, and z of t is t squared. So this is a three-dimensional function. So if I talk about my function, it looks like it's going to be position, right? So my position is going to be a position function, which is going to be x of t, y of t, z of t, right? So now that means that it's going to look like t squared minus 7, 5t, t squared. I'm just kind of giving you a bigger picture, right? It's just like a vector function. Actually, p would be like a vector function because it's got multiple components to it. You don't need to worry about that. We're keeping it all separate, but just so you can kind of have it as a bigger picture. Okay, so let me just take the derivatives for each piece because I'm going to need them for other stuff. So my derivative for x is going to be 2t. My derivative for y is equal to 5, and my derivative for z is equal to 2t. Okay, so now the first derivative of my position is our velocity, right? So now if I say b of x at 0 is equal to 0, right? B of x at 2 is equal to 4. B of y at 0 is equal to 5. B of y at 2 is equal to 5. B of z, oops, sorry, at 0 is equal to 0. B of z at 2 is equal to 4. Okay, so now if I look at things, I'm going to put things together. So B of x is equal to x of 2 minus x naught all over 2 minus 0. So I'm going back. So my velocity, my x component, I have to look at the change in position over the change in time. Okay, so this is going to be, I go back up to x2. So this is going to be 2. So 2 squared minus 7, right? That's going to give me minus 3. This is going to give me 0 squared minus 7. So that's minus 7 all over 2. And this is going to give me 2 meters per second. Can you guys see that? Do I need to zoom out a little bit more? Okay, and then b of y. I'm going to do the same thing. So this is y of 2 minus y of 0, 2 minus 0. So I plug these in. We have z, z of 2 minus z of 0. Sorry, can't see that. 2 minus 0. This was 4 over 2. Okay. So to calculate our velocity. Okay. Okay. Average velocity here. Between 2 and time t equals 2 and time t equals 0. And I forget, did they ask us to solve for things in terms of get our values in terms of other? I have some notes down in here too. So what I'm going to do is, so I'm going to go, so if x is equal to t squared minus 7, then t is equal to plus or minus x plus 7 radical. Plug that into y. I'm going to get y equals plus or minus 5 times radical x plus 7. Z equals x plus 7. I don't know. I can't remember. I don't have the questions in front of me, so I'm not sure like if they asked us to solve for it. It was question number 2. Question number 2. Question number 9 in Appendix A. Something like this. So we were given x minus 5 equals y to the 4th. X is equal to t to the 4th plus 5. This is just what I have in my notes here. So x is equal to y to the 4th plus 5, and y equals t. That so then I'm going to get the equation. Oops, sorry, t to the 4th plus 5 and t. That's how I worked it through. I don't have the question in front of me. I'm just looking at my notes. think on this one, it was going to be easier just to assign y equals to the parameter because y was being raised to a power, and then easier just to substitute and then solve. Solve for x and then do the substitution. You guys have any other questions? Appendix A, number 15. Sure. You guys will have this. I'm going to turn the page. Question 15. All right, so if we're given g of t, so this just means it's a vector function, which means it has multiple parameters, multiple components to it. So this is my x is t cubed plus 2, t cubed minus 5, and then t cubed plus 17. And then and we're looking for the derivative. I'm trying to find, and I just have my notes. So what's dy dx? X is equal to t cubed plus 2. So I'm going to solve for, so this is going to be x minus 2 equals t cubed. I take the cube root. I'm going to get t equals the cube root of x minus 2. And then I'm going to plug that into my y function. So y equals t cubed minus 5. Right, into here in order to get y equals. So then y is going to equal to right, which is going to give me x minus 2 minus 5 equals y. So y equals x minus 7. Okay, here. And now if they want dy dx, okay, I just take that derivative here, which is just going to equal to 1. Okay. And I think that was it. Like I didn't have to do anything. Oh, I see. Yeah. So they gave me all these different pieces here, right? And oh, at that particular point. Okay, whatever. So they gave me all these different pieces here for the equation, but then they asked me for the derivative of y with respect to x, which means I need to come up with an equation of y with respect to x and then take that derivative. So instead of saying dy dt, right, dx dt or dz dt at a particular value, they're just talking about dy dx, which means I have to do a substitution.
I have a quick question about this one. How
Yeah.
did point Q come into play in the question?
Yeah, I'm not seeing it. Let me bring up my question itself. So give me just a second. Work. Question 15. So it says calculate the indicated derivative at the point Q. I'll use the chain rule. Assume that as usual the first component. Okay. Yeah. So they gave us. It's kind of like a misdirect in this one because they said let me just make sure we read that right. dy dx. Yeah. All right. So it's a little bit of a misdirect. So what they wanted was they said we've got this function. It's a multi-component function, and we've got this particular point Q. Right. That's happening. You know, like x, y, and z components to it. So my x of t, my y of t, and my z of t. Now, what they were asking for is dy dx, right, at this particular value. So this is like y prime, or you can think of f prime of x equals 1. So I'm going to go f prime, right, wherever my f prime of x, f prime of 10. Well, my derivative is equal to 1. So regardless of whatever my x value is, right, my derivative is always going to be equal to 1 because that's the nature. Like when in order to get y in terms of x, to do this derivative dy dx, right, then basically as I'm doing this derivative, the x's, all the powers of the x cancel out. And so then I'm just left with a linear function. So then whenever I take this derivative, my function is just going to be a constant term, right? Let's pretend, we'll just pretend for a minute that my y equals x squared minus 7. Say, for example, I take that derivative, I'm going to get 2 times x. Now, when I plug in my x value of 10 into my derivative, I'll actually get like a number that's going to change as a function of what point we're at. But here, my derivative is always going to be a constant term. So to say, let's do it at this particular point, well, it's kind of a moot issue because I think it's going to be the case. These are all cubic powers. So whenever I plug in, what I'm going to solve for t on all of these and plug them into whatever. So if I go like, this is dy dx, but if I did like, you know, dx dz, say, for example, and you take the derivative of x with respect to z, again, I think that my values, I think all of these derivatives, all these functions are going to be linear because of the nature of, like these are all cubes, right? So then I'm going to take the cube root and then I plug it in. It's just going to become linear. So I think that this was a little bit of a misdirect, right? Because our derivatives are linear, essentially. Unless I did dx dt, right? And then I plug it in and I'm looking at, but then I need to be finding, you know, assuming these are values of t. I think those are values of x, y, and z. So it's kind of a misdirect because we don't, you know, we don't have that. Does that make sense?
Then I also have another question about 14 because the derivative dz dx is 2x, not a constant. So
Right.
how would we apply point Q to it?
Yeah, okay, so we'll do that as another student's asking the same question. So let's do question 14. So this one, let me write it down. So this is b of t equals t squared, and we're doing this at point q equals 1, 1, 1, and we're looking for dz dx. So now let's do this out. So my x of t equals t, my y equals t, and my z equals t squared. So I want dz, I want z in terms of x, right? So this is going to be, this is equal to x. So if I plug this in, if I plug in x for t, right, this is going to be equal to x. This is going to be x squared, right? So z equals x squared. Now, if I do dz dx, so the derivative of z with respect to x, like you see how we did this, x is equal to t. So I can plug that into each of these here. I'm going to get x and x squared. So here I get z equals x squared. Take that derivative, I'm going to get 2x, right? But now I want to look at when x is equal to 1 right here. That's where I'm getting that 1 value from, right? So then this is going to become 2 times 1. So dz dx when x is equal to 1 at this point is equal to 2. This is a 3-dimensional function. It's going to look like, it's going to look like, right, if this was like x, y, and z squared, say, for example, right, it'd have basically kind of like a linear, like I have x, y, and z. You'll get this when you get into calculus 3. You'll start getting into like 3-dimensional plots, but you're going to get x and y on your axis on the floor. So that'll just be a line, y equals x, right? And then here on my z-axis, it'll be squared. So it's going to kind of come up as a parabola like this. Okay, it's hard to imagine, you know, the 3-dimensional shapes, but in our basically looking at taking the derivative of my z variable with respect to my x-axis, with respect to my x variable, at this point here, where x is equal to 1, then I plug in 1 for x, and I multiply it by 2, and I get a 2. Does that make more sense? It's different. We're starting to think 3-dimensionally, you know. And then, like I said, when you get into calculus 3, you start to think about how do I do all this stuff? How do I graph it out? What does it look like? Okay. But a lot of these are kind of like manipulating the equations and then solving for the different variables. Okay. Any other questions, you guys? Happy to keep answering them. In class, I'll just tell you, if we were like in an in-person class right now, and if we were done answering questions, we would take our quiz, right? We're not going to take the quiz in class. The quiz is going to open up at noon today, okay? But if nobody has any other questions, then we can end early because you guys actually have a quiz later today that you need to Appendix A, question 6. Okay, let's do that really quick. Okay, so Appendix A, question 6. So we're given a vector function, looks like our position function. So t squared minus 7, 5t, and then t squared. And then our v of t, our velocity is the derivative of each of these. So I take the derivative of my x, I'm going to get 2 times t. Take the derivative of my y, I get 5. Take the derivative of t squared, I get 2 times t. And then this is at t equals 2. So my velocity at 2 is equal to 2 times 2 is 4. This is 5 no matter what, and this is 4. This is meters per second. Okay, so what this means is we have an x, y, and a z axis, right? And we have a position as a function of time, okay, that has an x function, a y function, and a z function. Now we have a velocity, right, which is our derivative of our position as a function of time. Now the velocity at a certain time, right, is the derivative of each component. So this is x prime, y prime, and z prime, right? And then we just evaluate at whatever t value we're looking at. Our acceleration is our derivative of our velocity. So I take the derivative of 2t, I get 2. Derivative of 5 is 0. Derivative of 2t is 2. And this is at t equals 2, which is my acceleration at 2. Sorry, that's at 2. Wherever I see a t, there's no place to plug in a t. So my acceleration is constant at all times. Acceleration is constant, meters per second squared. Okay. Our speed at t equals 2. So speed is the magnitude of our velocity. Okay, which means what I need to do is I have to take each component, square it, sum it up, and then square root it. So my speed is always going to be a positive number. It's a magnitude. So we're doing this at t equals 2. So I'm going to take this value here. So this is 4 squared plus 5 squared plus 4 squared, because we already calculated it. They said at time t equals 2, which we already did. So I take this here. So it's 16 plus 25 plus 16 square rooted. Leave it as a radical. I got radical 57, and this is meters per second. Okay. Okay, guys, what do you think? I have office hours too today at 1 o'clock if anybody wants to come and ask any questions then. Okay, guys. Is the quiz on both Appendix A and 2.6? So this is just on 2.9. Appendix A is going to be next week, right? So I'm going to lump that in with stuff that we're going to cover on Monday. So we'll have new material on Monday, and then whatever we cover on Monday plus Appendix A will be on the quiz next week. Today is just 2.9. It's kind of a light week. We had a test last week. That's why. It looks like somebody asked a question, Appendix A number 10, I think, is that the question it looks like? Okay, so let's do Appendix A number 10. Okay, so Appendix A number 10. So this says y squared equals x cubed. And so this is kind of a funny one. Yeah, they wanted you to parameterize it, I think, is the question. So I was kind of playing around with different things. So if I do x is equal to t squared, right, then that'll maintain this this range here. So then what I get is I I'm going to go, if I plug it into this thing right here, so I'm going to go t squared cubed, right, is going to give me t to the 6th, right? And then and this will be t, yeah, okay, and then y is going to equal t, oops, sorry, y equals t cubed, because then if I plug it into this, then I'm going to go t cubed squared is going to give me t to the 6th. So that'll make this equality true. T to the 6th equals t to the 6th, right? So that's what I want. So then that's how I kind of played around with it. So I got t squared t cubed was the parameterization of this function here. And so I think they gave us this function. They said parameterize it, right? And so basically I kind of had to play around with what values of t. Like if I couldn't do t cubed equals t squared. Like if I said x equals t, right, then that would make it t cubed, and then it would just kind of be weird, like it wouldn't quite work out. And so actually, although it did give me a clue, so if I make x equals t, then t cubed, and then if I have to square it again, it just like it kind of got weird. So I kind of looked at like how I could make, what values could I make these equal to each other, because that equality had to be true. So t to the 6th had to be equal to t to the 6th, and making x equal t squared and y equals t cubed, right? So the other one, so then basically the exponent here would be equal. So that's kind of how I did it. I just kind of played around with it. Okay. What do you think? Okay. You guys have any other questions you want to ask about homework stuff? Okay. If there are no more questions about the homework, then we can just end the class early. Although I kind of say early in quotes because you guys have a quiz later, okay, which will be a 30-minute quiz plus 15 minutes to upload, okay? Take pictures and upload onto our Canvas page. So keep that in mind, okay? When should we expect to get our midterms back? And I thank you for being patient about that. My goal is to get them graded completely. I'm still grading them. It just takes so long to grade them electronically. So my goal is to get them graded this weekend. Like finish the grading this weekend, and then I can post them this weekend. So yeah, because I had to download all of the files, and then I have to grade them separately. So I can't even grade them on Canvas anymore because Canvas won't let me grade them on Canvas. I have to download all the files and then work on them like on Adobe Acrobat or on some kind of a JPEG editor, and then I have to record the data, and then I have to upload your corrected file to Canvas, and then I have to post the grade. So it's actually like a lot more work than it is if I just had a paper exam, but whatever. So I thank you for being patient. It just, it takes longer with the electronic stuff. So my goal is this weekend. Okay, guys.
Thank you so much. Have a good day.
Thanks, you guys, and have a great weekend and stay safe. Have a happy Halloween.
You
And
too.
I'll see you guys again on Monday. Okay.
Thank you.
Take care.
Thank
Bye-bye.
you.
Bye.